The first periodic trend that we're going to talk about is atomic radius, or the size of an atom. So atomic size is defined as the distance between from the nucleus to the outermost electrons of an atom, which is the radius. And it is measured by taking an element in the solid state where the atoms are touching each other and measuring the distance from one nucleus to the one next to it and cutting that in half. So half the distance between two nuclei would be the radius of that atom. And this is done by something called scanning electron microscope, which is SEM. And these are pictures. These are pretty old pictures. They've gotten better over the years of diamond, which is carbon, and silicon. And you can see that the silicon is a little bit bigger. And you can see that the atoms are all lined up in the solid state. And so they use this type of device to measure the radius. So there are two factors that affect the size of the atom. And that is the nuclear charge, which is the number of protons in the nucleus, and the number of inner electrons. Those are the electrons that are on the inside electron levels, the ones that are filled up. And that combination leads to, the combination of these two factors is something that we call ZEFF, Z-E-F-F, which is effective nuclear charge or effective nuclear pull. It is how much the nucleus is pulling on the outer electrons, because the more it pulls, the smaller the atom will be. The net effect of these two factors depends on something that is called shielding. And what shielding is when the inner or the filled electron levels, the ones along the inside closer to the nucleus, when they block the force of the pulling of the outer electrons. So these electrons on the outside are pulled by the nucleus, but these inner electrons are in the way. They're blocking the force of the nucleus. So we say that these inner electrons are shielding. And the amount of shielding is based on the number of closed up or filled electron levels that you have in an atom. So size changes as you go down a group. It increases as higher and higher levels of energy levels are filled, more energy levels are filled, the electrons are going to get further and further away from the nucleus, and the atom gets bigger. The trend that's the most tricky to explain is how size changes across a period. Going across a period, the size decreases, and that is because as electrons are added, they are added to the same energy level. We're not going higher and higher in energy level. So shielding remains constant. Yet the nucleus is getting more protons, so the nucleus has more pull, but the same amount of shielding. So we say that there is increased ZEFF, or increased nuclear charge. So the nucleus has a little bit more power as you go across, and it makes the atom smaller and smaller. So this is a summary of the main group elements, the A group elements. And you can see going across, it gets smaller as you go across. So the noble gases would definitely be the smallest in their period, and the alkali metals would be the largest in their period. There's a really big difference. Lithium is on this end, and then going all the way over, neon is on the right side and much, much smaller. And then as you go down a group, the size always gets bigger. And notice there's this regular thing that happens when you get smaller and smaller, go across to the noble gases, go to neon, which is pretty tiny. Then you go to the next element, which is sodium. It is much bigger, huge increase in size, because we have gone up an energy level, and all those electrons that were added in the second period are now shielding, and we've added an electron to the third energy level. so it's much further away, much larger. The trends for the radius in the transition elements, they are still there. As you look across, you do see they definitely get a little bit smaller as you go across, but they're not as regular. They're definitely harder to see the trend. The trend up and down is still there, however. So as you go down, they get bigger, but the smaller going across a period, it's just tougher to see in the transition metals. D orbitals, some weird things happen with d orbitals, so not as regular of a trend. Okay, cations versus atoms, neutral atoms. So it's useful here to talk about electron configuration. So if we look at sodium, it has 11 protons and it has this electron configuration. The 3s1 is the valence, or the outer electrons. The ones on the inside in energy levels 1 and 2 are inner electrons, which are shielding. So that's plain old neutral sodium. If we make the cation for sodium, we are going to take away this electron, the valence electron. So here's sodium cation. That electron that was in the 3s is now gone because it was taken away to make the cation. So now these electrons in the second energy level, these are valence electrons. They are the outer electrons, and there's fewer electrons shielding, but the nucleus still has the same number of protons. So the nucleus still has the same amount of pull, but you can think of it as having much less work to do, but the same amount of pull. So it's going to pull a lot more, and the size goes way, way down. I mean, much more than a little bit. If we look at sodium, the left side, the blue one, is neutral, and then the one on the right, the little white one, that's the cation. So it's around half the size. It goes from 186 to 102, not quite half, but definitely quite a bit smaller. Okay, the opposite happens with anions, as you might expect. Here we're going to look at fluorine. Fluorine has 9 protons. It's got the 1s2 in the inner shielding electrons, and these are the valence, or outer electrons, 2s2, 2p5. When it gains 1 electron, it makes an anion. That electron's going to go in the 2p to make 2p6. So now what's happened with fluorine anion, or fluoride, we have got the same number of protons. So the protons have the same amount of pull, but they have a little bit more work to do. There's 1 more electron, and so, but no more protons to pull more. So the size goes up. The pull is not as much. And we can see that in the diagram. Let's look at fluorine. So fluorine on the left is the red neutral fluorine, and then on the right is the -1 anion fluorine, and you can see that it goes from 72 to 133. So not quite twice as big, but close to twice as big. It's definitely quite a bit bigger when you make the anion. So the cation gets smaller and the anion gets bigger.